This problem involves finding the magnetic field from several different sources added together, and we know magnetic field is a vector, just like electric field, just like force, so it will add together as vectors add together. If I were to, in this case we've got 4 wires arranged in a square, 3 of them are coming up out of the plane of the paper, and this one in the bottom right corner is going downward. That's 3 of the currents, I should say. We're given the current, we're given the distances, which are all the same distance that's in a square, and we find the magnetic field at the center. Okay, so I've drawn our situation right here. I'm going to label these wires 1, 2, 3, 4, so we know what we're talking about. And we know that these vectors, if we want to find the magnetic field at P, or I can just, instead of saying the sum, I could say the magnetic field at P, which is a vector, is going to be the vector of magnetic field due to 1, 2, 3, and 4. But I put these vector bars here that are very important because I cannot just add the magnitudes. These are vectors, so they have to add as vectors. So that means we're going to have to break everything down into x and y components and add it as add x and y like components together. But let's first analyze the situation and look visually at what's going on. So current 1, for example, actually let's do current 4 first because it's easier for my wrist in this position. If we do the second right-hand rule, I'm pointing my thumb up out of the page. The current is going to curl around counterclockwise around 4. So that means, did I say the current? The magnetic field will curl counterclockwise around the wire 4. Okay, so that means if I expand it out, remember it's decreasing in magnitude with 1 over r squared, but the shape stays the same. Everywhere around this wire it's going to circle in a counterclockwise fashion. That means all the way out here, the circle that passes through the point P is going to create magnetic field due to B4, and it's going to be curved in that direction. Now the same thing is true about 1 because it's doing the same thing. You point your thumb in the direction of the current, your fingers curl in the direction of the magnetic field, and that continues all the way around. So B1 curls like that, and if you extend B1 all the way out to this point, you will have a magnetic field that looks like that. Okay. Same thing with 2. It's also going counterclockwise, so I point my finger in the direction. So it's going, B2 is going to curl around this direction, so extend that out to this bigger circle that passes through P. It's going to look like that. 3 is different. Point your thumb downward in the direction of the current, and my thumb downward in the direction of the current, and my fingers curl in the direction of magnetic field, which now is going to be clockwise because the current has changed direction. So if I extend that circular magnetic field outward, I get something that looks like that. So I'm going to draw this again. But instead of this circular magnetic field where you think any point along this line is going to represent a vector for the magnetic field, I'm going to draw this whole thing again. One, 2, 3, 4, and this is point P. The magnetic field due to 3, remember it's curving this way, so tangential to the curve, it's going to be like that. So since it's circular, it's always going to be at a right angle to the line connecting it, the R vector connecting it to the wire. If we look, maybe go right across to the other side, B1 curves like this, tangential to that curve is, oh, what do you know? It's in the same direction as B3. B4, curling around this way, so tangential to that line of connection will be in that direction. And 2, remember it's circling this way, so tangential to this big circle here and at a right angle to the R vector is B2. So I'm actually going to erase these lines connecting it to the wire, just so make the vectors a little more clear. So the current is the same in every one of these wires. We know every one of these wires is equidistant to this point P. So what does that mean? Well, B2 and B4 have to cancel out. Plus B4 equals 0. The magnitudes are the same. They're just in different directions, so they cancel out. We are left with then, and you can prove that if you want to, but it's just because B from a wire is equal to mu naught I over 2 pi R. R is the same because they're equal distance. I is the same, you're giving that in the prompt. The only difference is the direction, so they have to cancel out. So that leaves us with these two additive magnetic fields, B1 and B3. Make my dot really big here. B3, B1. So in this case, the question just asks for the magnitude. So all I have to do is add the magnitudes of the B1 and B3 together. So the sum of the magnetic field is equal to just magnitude of B1 plus magnitude of B3. We know these are going to be the same magnitude because for the same reason I discussed over here, same current, same distance. But you know, in case you wanted to prove it, we can do that. So let's first think about the distance, because this is going to be mu naught I over 2 pi, I'll call R1, plus mu naught I over 2 pi R3. The distance between, well, I drew my triangle backwards. One, 3, I need to find P in the center. So R1 is going to be this, and R3 is going to be that. Since these are just the same distances on each side, then we know R1 plus R3 equals square root of 2D. You can prove that by just a triangle with two equal sides. An isosceles right triangle means the hypotenuse is going to be square root of 2D. And we know since that is right at the center of the square, then it's going to be in the center of the hypotenuse. So R1 equals square root of 2 over 2D, and that equals R3. So this equals, factor out mu naught I over 2 pi, 1 over R1 plus 1 over R3. Why did I do that? I already showed that they are exactly the same. So this is just going to equal mu naught I over 2 pi times 2 over R1, or mu naught I over pi R1, which R1 is square root of 2 over 2D, I can make that a little nicer, so it's 2 over square root of 2 u naught I over pi d. And if you want to put in the numbers, I pull the pi out too, so I get all the constants together. 4 pi times 10 to the negative 7 newtons per ampere squared times 8 amps over 0.020 meters. Sum of the magnetic field then is 2.26 times 10 to the negative 4th Tesla. What if, and we know it's in that direction. So what if the problem had asked us for the direction as well? Well, we know B is in this direction, sum of B, and we also know that it's a similar triangle to the triangle as a whole, where this is D, and this is theta. So those two thetas are equal. So the vector B is just B cosine of theta I hat plus B sine of theta j hat, and we know cosine of theta, it's equal to cosine of pi over 4, right? Because it's just half of pi over 2, so, or cosine 45 degrees, either way. So that is equal to square root of 2 over 2. And we also know this equals sine of theta, because 45 degrees, or pi over 4, right there in the middle. So then B would equal the magnitude of B, which is 2 over square root of 2 u naught I pi d, and I'm factoring this out. Cosine of theta, just square root of 2 over 2 I hat, plus sine of theta, square root of 2 over 2 j hat. So there's the same term in each one. That's going to cancel out both of those factors. Cancel out the square root of 2 and cancel out the 2. So B equals mu naught I over pi d I hat plus j hat. But the question didn't ask for this. This was just an extra freebie.